you all picked a few points on your hyperbola, and then very carefully you measured the distance to each focus. Ooh, that's better. Okay. What I would like you to do now is I would like you to take the difference of the measurement. So from one point, you have two measurements, subtract them to where you get a positive number. From another coordinate, you have two measurements, subtract them so that you get a positive number. I'll give you a moment to do that. I was like, what are you doing?
Are they supposed to all be one? Is that supposed to be like the
One, but they should be the same.
yeah,
Oh, so it's supposed to.
they're supposed to be like the same numbers.
Oh, another point.
Mine's like
Oh.
But that doesn't make it any better, that made it worse.
Are you noticing anything?
Now waiting for it. So then it's 1.5.
Now take into account there is a little bit of room for
Oh,
error
mine's
because we're
1.5.
measuring pretty small distances. But what's true about the difference each time you subtract the distances? You should be getting the same. Okay? Now, in a perfect world, we would all be getting the same exact number because you all have the same exact hyperbolas. But some of us maybe don't measure as well as others. Some of us use centimeters, some of us use fractional inches, okay? But you should be seeing that to a certain extent, when you subtract the two distances, you get the same measurement, okay? Do you think that has anything to do with the definition of a hyperbola?
No.
Not at all? Okay, so when we talked about ellipses, right? When we talked about ellipses, we had foci that when you took the distance and added them, we had the same number, right? You remember doing that with our dental floss? Okay, that wasn't used by anything. Okay. Well, now we have a hyperbola. Okay, and a hyperbola is defined as the set of all points where the difference of the distances from two distinct points is constant. That's what you just measured. Okay, so I'm going to give you a moment to write down the definition and draw the picture. And I'm going to come around and grab your ruler so there's not a distraction. Well, getting time to get some girls on.
What did he do?
He got this little thing that So very much like an ellipse, a hyperbola has a center. It has vertices, okay? Along the axis where the center and vertices are lie two foci, okay? Notice, however, that the foci here are further away from the center than the two vertices, okay? That's different from when we have ellipses, right? The foci are closer to the center for the ellipse, but here the foci are further away from the center in a hyperbola, okay? Fun new addition, we have asymptotes that go through the center. Do not panic about the asymptotes, okay? We are going to use a pretty simple method of getting them drawn. And then I'm going to remind you about point slope form so you can write the equations of those points. I don't know what's going on with this right here. I can't get it to go away. But we have the major axis and minor axis in an ellipse. We call the axis where the foci, vertices, and center are in a hyperbola the transverse axis. So this is a horizontal hyperbola that I have drawn up here because the transverse axis is horizontal. Okay, center, vertices, and foci are all horizontal from each other. Okay. When we talk about these asymptotes, I want you to remember do you remember point slope form for a line? Okay. You've heard people say it, point slope form? Maybe? Okay. I know that you are very used to y equals mx plus b, slope-intercept form. I tell you, that's wonderful. Okay? However, you're growing up. Okay? And when you get to calculus, and I think maybe even statistics, but I know in calculus, we really only use point slope form. And it's actually going to make your life easier. Okay? It's going to make your life easier because I'm not going to ask you to reduce it down. I'm going to ask you to leave it in point slope form. So I'll remind you that point slope form is y minus y1 equals slope times x minus x1. When we get to write our asymptotes, you're going to leave it in that form. Okay, I'll tell you what to plug in for x1, y1. We'll determine slope, and then you'll just leave it in that form. Which I'll just disclaim it right now. It's going to be different than what the book does, but this way is easier. Okay? You like easier? Okay, it also makes more sense. When we get into it, we'll be able to visually see the center using the point slope form, and I like that. Okay? So, let's talk about the difference in a vertical and horizontal hyperbola and how we recognize their equations. Okay, so let's just hop back in time a moment. Parabolas, we knew we had a parabola because of what in our equation? X or y being squared, but not both, right? Okay, then we went to ellipses. We knew we had an ellipse because both of them were squared and But what if they're all like mixed around? It's not in standard form yet. Well, it's true about their signs. They're the same. Okay? Now we still have an x squared and a y squared, but now their signs, their coefficients are going to be different because we have subtraction. Okay? Does this look similar to that of an ellipse standard form? What's the only difference? We have subtraction in the middle. Okay? Also, it doesn't matter who's bigger, A or B. Different way to find c squared because of some geometric properties that we won't get into today. So if you'd like to know, I can show you. Okay. What do you notice about c squared? We know that, right? Okay, it's like a right triangle. Okay, so that's exciting. Okay. What I'd also like you to make note of, so you'll see this when we get to our vertical example, but a squared is always going to be associated with the direction. Okay, so since this is a horizontal hyperbola, the x squared is the positive one and it has a squared underneath. Okay, A is always going to give you how far away the vertices are from the center. Okay, and C, just like an ellipsis, is going to give you how far away the foci are from the center. So whether you draw a new picture or not, at least add to your picture from before that the vertices are A away and the foci are C away. Does anybody want to make a prediction about the difference in the formula for horizontal versus vertical?
Y minus X, showing it.
Eli says y minus x. Sound reasonable? That's exactly right. But please notice that a squared remains with the positive variable. Notice how the y minus k is squared, so we write it first. Or it's positive, so we write it first. A squared's underneath of it because A is always telling us the vertices. Okay. Mrs. Holding, you haven't told us anything about B. What do you think B is going to help us find? The asymptotes. Okay. B is going to help us with the asymptotes. And the asymptotes will then help us figure out how wide to make our branches. Is that what you're trying to do?
That's what I was going.
Okay. The asymptotes will give us the shape for our branches. Okay. You won't need any other points on there besides the vertices. Okay. So what we're going to do is just hold on before you write anything down. from our center, obviously we'll go A away for our vertices, we'll go C away for our foci, but then what we are going to do is we are going to, these aren't actually coordinates, but we're going to go B away from the center. We're going to make an imaginary rectangle, and then through the diagonals of the rectangle, we can draw our asymptotes. So whatever you want to draw, you can. We make a rectangle out of A and B so that our asymptotes can be drawn through. Yeah, you're not so sure about this. It's really not. It's not any more work than an ellipse. Except for you writing down the equation of, yeah. Okay, so we're going to do two examples just like we did on Friday. One is going to be an example that's already in standard form. One is going to be an example that we have to get into standard form. Okay, we're going to start out with a very, very simple one. Okay, just to kind of get the hang of things. And then our next one will be more intense just because that's how it goes. Okay? Does everyone have what they need written down, drawn out, labeled? Give me a thumbs down if you need more time. Okay, here we go. Write it down. X squared over 9 minus y squared over 25 equals 1. Turn to your neighbor, tell them which direction you think it opens and why.
Wait, is the A have to be diagonal?
No, it doesn't. It's
Diagonal.
It's horizontal.
Okay, Lindsay A, which direction does this open?
No, horizontal.
Why?
Because the X is
This is a horizontal hyperbola. The x is first. Lindsay, I'm going to have you be a little bit more specific. It's first because it's positive. Okay, I could be annoying and put negative y squared over 25 plus x squared over 9. That'd be kind of mean. But we put the positive one first. But the x squared is the positive one. Therefore, it's horizontal. It doesn't matter that it has the smaller denominator. Okay? The center. This is why this is a nice, simple example. Where's our center? Okay? We have no h and k, so our center is at 0, 0. All right. Now, for our vertices. Okay. Let's go ahead and identify A and B. Okay. Since the denominator of our positive variable is 9, that means A is 3. We have minus y squared over 25, so B is 5. So horizontal horizontal, A is 3. We are going to go horizontally 3 from the center. I'll let you decide. Would you like to do asymptotes or foci first? I hear vote for foci. Foci? Okay. So using A and B, we know C squared is A squared plus B squared. Okay, that is a difference from ellipses. We just have to remember which one's adding, which one's subtracting. Okay, so we have 9 plus 25. I don't know, I wrote 2. Which is 36? No, 34. I got excited. I wanted a nice number. 34. And that does not have any perfect squares in it, does it? No. So our foci are horizontally radical 34 from the center. Okay, radical 34 is just shy of what whole number? 6. So we're going to go from the center, 1, 2, 3, 4, 5, almost 6. 1, 2, 3, 4, 5, almost 6. Those are your foci. Okay, so from 0, 0, we went right, radical 34. From 0, 0, we went left, radical 34. Okay, I will remind you that in a hyperbola, your foci will be further away from the center. In an ellipse, they will be closer than the vertices. Okay, so that should maybe, give you an idea. If you mix up your C squared formulas, okay, you at least know which ones should be outside versus inside the vertices. Okay, let's talk about our asymptotes. Okay, green is my light color. Okay, what I do in green is what you should do very lightly because it's actually not a part of the graph. Okay, so my B, which is also under the Y, so we orient vertical movement. Okay, our B is 5. So vertically, I'm going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 from the center. Okay? It almost looks like we can make an ellipse out of those 4 points. Okay, but we're not going to make an ellipse. We're going to make a rectangle. So very lightly, I want you to draw a dotted rectangle using those B coordinates I had you draw and your 2 vertices. They're like the 4 points we would have made an ellipse out of, but instead we're going to make a rectangle. I guess maybe I should have let you keep your rulers. Maybe I'll do that next time. Because now we're going to draw lines. Okay? Our asymptotes conveniently go through the center because they're going through our diagonals. Okay? So basically you need to connect corner, center, corner, corner, center, corner. And just so we can complete the graph, asymptotes give us our shape. So you need to draw your hyperbola approaching those asymptotes. Yeah.
How do you know what the constant is?
What constant?
The one where it's like so much away on the hyperbola from the...
Oh, it's going to be different every time. So kind of like we did with our ellipses. You know when I had that picture that I made bigger, I made smaller? That distance remained constant, but it was different sizes depending on the size of the ellipse.
So there's no way to figure it out from the equation.
I would say you would have to, well, there would be a way to find it from the equation. I knew at one point. I think it's double A. The difference between, yeah. Yes. Whatever, but that would be like the units you're using here. So however distance that is, it'd be 2A with that measurement. Do you see what I'm saying? Okay. Good question. Now our asymptotes. I'm going to go back to here. We're going to use this. I will tell you that y1 and x1. What point do both asymptotes go through? This center. Okay, for our example, yes, 0, 0, but for any problem, it's going to be this center. So you're going to use the center as x1 and y1, and then all we're going to have to do is look at the slope. Okay? From this point, we go up b. Okay, we go up 5 and over 3, right? So this y minus 0 equals 5/3 times x minus 0. Okay, y equals 5/3, x is fine. And then what about the other? What's going to be true about the slope of the other line? It's just going to be the exact opposite. So here's another time where if you want to write that those two equations as one, we could just say our slope is plus or minus 5/3. Okay. Now, it is not always going to be b over a. It's b over a because we have a horizontal hyperbola. When we have a vertical hyperbola, it's going to be a over b. So what I need you to do is I need you to look at your picture and determine what's happening. Yes? In this case, I would have no problem with y equals 5/3 x. In any other case, leave it. Okay, if there's a 0, that's fine, simplify it down. But I do not want you to multiply this through and add that over. I do not. Because we can very easily see that our 0, or our center is HK. All right, awesome. Let's get through another example. This one, I'll just tell you right now, it's going to be vertical, okay, because I want you to see both kinds. But as you're writing down the example, do you notice how we have 16y squared minus x squared? Okay, that's our tip that it's a hyperbola. Because we have x squared and y squared, but they have different signs. What do we have to do, though, to get it in standard form? Complete the square. You know how some of you are a little iffy about completing the square last week? We're getting lots of practice, aren't we? Yeah. Okay. We do need to be careful, though, but it's going to be very similar to that of an ellipse problem. All right? Here I have 16y squared. So A, I need to factor out the 16 from the y squared. And I also need to factor it out of 64y. So that would be 4. Yes? No. You good with that? Okay. Okay. Now, for my x squared, our coefficient is still not positive 1. It's negative 1. So we do have to factor out a negative 1 from our x squared, which means we also have to factor a negative 1 from the 2x. And we'll have to add our mystery numbers to the other side along with the constant. Now, You're always going to have to factor out a negative here because it's a hyperbola, whether it's -1 or -10 or -15, I don't know. But please be careful when you're factoring it out of the linear term because that's going to change the sign. Okay? All right, what completes the square here? 4, but it's 4 times 16, so we have to add 64 to the other side. What completes the square here? 1. Another time where it's so easily to overlook something. 1 times -1. You need to add -1 to the other side. So what we end up with is 16 times y plus 2, the quantity squared, minus x minus 1, the quantity squared, equals, oh, that's nice, okay. Just like with ellipses, we need this to be 1. Okay, so we're going to go everything based off of this guy right here. Okay. Please be careful when you identify the center. The center is 1, -2. I know that's not the order in which you see it, but we have to grab x then y. In this case, A is 1 and B is 4. Okay, we have 3 minutes left, so I'm just going to kind of push it, okay? I want to get to the asymptotes here. So for our vertices, I need to go vertically 1 from the center because A is 1. B is 4. That's helping us get our asymptotes. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So since our B is associated with X, we're moving horizontally B. Really lightly make that rectangle. And then through the center and corners, oh, that was just not very good at all. I really apologize. I don't have like a ruler I can use, but just does it. Oh, it's the wrong way.
No, I know.
Oh, I was like, wait, no, this is vertical. Don't make me nervous like that. Caleb did the wrong way. Okay. Whew. Okay, so now, center to corner, our slope is up 1 over 4. Our center is 1, -2. So what I'm going to have you do, I'm going to have you do y minus k equals slope times x minus h. So our coordinate is just the center because both lines go through the center. And then I counted my slope to be 1/4. So one has a positive 1/4, one has a negative 1/4. All right, all the way